So let's multiply. When we multiply, I don't need this. So we get x to the fourth over 4, right? First multiplication. Then if you look, for example, if I do the further ones, this one times that one, the x squared top and bottom cancel out, and you only get negative 1/4. Same thing with these two, with the two close ones. You also get another negative 1/4. And that last one, you square it, you get 1 over 4x to the fourth. Good? All right. Now, of course, negative 1/4. If you do two of them, you get negative half, so that's a negative half. X to the fourth over 4 plus 1 over 4x to the fourth. And where is this coming from? This is the square of that, right? That's the complete square of that expression, the binomial to the second. Where is the negative sign is coming from? The negative sign is coming from that negative sign. Now, someone open the mic and answer this question. If that negative sign was a plus, what would be the value of this middle term? Waiting.
Be positive 1/2.
It would be positive 1/2, exactly. That means if I have positive 1/2, I can factor it back to this guy, right? Well, let's see what happens if under square root you add 1 to it. So under square root, I have 1 plus y prime squared, which is 1 plus that expression right there, right? That's y prime squared. So it becomes x to the fourth over 4 minus half plus 1 over 4x to the fourth. And as you can see, it is what we want to be, because half minus 1 minus half, it's plus half. Plus half plus 1 over 4x to the fourth. Right? And we already know by the argument we made up there, this is the complete under square root is the complete square of x squared over 2 plus 1 over 2x squared, and you're taking the square root of that, they cancel out each other, and eventually becomes x squared over 2. Let me go ahead and raise a parenthesis. It becomes x squared over 2 plus 1 over 2x squared. So that's how under square root. Question on that? And this was, you're welcome, Alex. This was very similar. I want to say it's exactly one of the questions, one of the 4 questions I gave you last Monday. Talked about curve length, right? And I did tell you that they all follow the same pattern under square root. When you add 1, it becomes the same one with the positive sign, and you can complete the square. Pull it out of the, square root. Anything else before we begin chapter 10? Sequences. No? Okay. All right. So for the rest of the semester, which I'm probably never going to see you again, we'll talk about sequences and is it all? Sorry, guys. Sequences and series. Okay. And I'll give you the definition. Probably you know what a sequence means, and then series basically it's the sum of the terms of a sequence. So sequence is, I mean, the name is self-explanatory. It's a sequence of numbers, and there are infinitely many of them. Then you add all these terms up, and you get a series associated to that sequence. And then you want to, check the behavior We study the behavior of these series when they converge to a number and when they diverge. Okay, so before that, we start with a sequence, which are the terms of series. So here we go. 10.1. Sequences. And we start with this definition. And since it has infinitely many terms, I'm going to go ahead and use the infinite sequence that guy is, so it can be seen as a function, is a function. I'm going to call it A. Let me write down this notation. I'll explain what it means. It's a function from natural numbers to real numbers. Basically, that's the set of inputs. For example, you have A of 1, A of 2, A of 3, and so on. Somewhere, you have A of 50. And the output is a value in the real number set. For example, A of 1 to be half, A of 2, 1/4, A of 3, 1/8, okay? And so on. And A of 50 is, another number. So as you can see, the inputs 1, 2, 3 are coming from the set of natural numbers, the numbers we use to count things. 1 chair, 2 students, 3 cars, and so on. But the output is not a natural numbers. You never say half a car or 1/3 of a student. Okay, so so this is the set of outputs, right? Basically, it's a machine. Okay, A of n. When from this side you're inserting the input, and that side it's giving you output. But the only restriction for this guy comparing to other functions is that the inputs are natural numbers. So 1, 2, 3. These are the numbers that get in, and the output or the corresponding values to these guys are real numbers. Okay, and normally these real numbers follow a pattern. Not all the time. Doesn't have to be. Okay? Probably you have seen puzzles that find the next element or number in that sequence. So if there's a pattern, you can easily figure out the next number, but it's not actually. Okay, so the incomplete definition. An infinite sequence is a function A from natural numbers to R. Okay, and let me finish by this way. We normally write A of n this way, A sub n. So notation wise, these two have the same meaning. I mean, of course, symbols are different. This is an index of A, and here n, it's written as an input of A, but they have the same meaning. For example, these two have the same meaning. Both mean the first element or the first term of the sequence. Okay. So they both have the same meaning, A sub 1 or A of 1. But from now on, we're going to use A1. Okay. So the sequence up there, instead of A of 1, I'm going to write it A sub 1, A sub 2, A sub 3, and so on. In general, A sub n. This is called the nth term of the sequence. Nth term of the sequence. And you can imagine this is the first term, second term, third term, and so on. Okay. Questions so far? Okay. Nobody else has question? The next call. Let's look at, a couple examples. So let's start with this. A1 could be, maybe 2. A2 be 4. A3 being 6. Can someone tell me what the next element is? A sub 4 is? 8. Good. Somewhere along the line, in the middle, like that, I'm gonna miss a lot of terms. And then let's see, what is a 20th? The 20th term of the sequence? 40. So as you can see, there's a pattern. Alex saw it. Each term is a double of its index. Like the first one is 2 times index 1. The next one is 2 times 2, 2 times 3, 2 times 4, and so on. So that's what I mean by pattern, right? So in general, a sub n is 2 times the index n. Here index is n, and then 2n. Okay, that's just an example. It's not going to be like this one all the time. Let's do another one. A1 being 1/3, okay? A2 being 1/9, A3 being 1/27. Can someone tell me what the fourth element is? 1 over. You tell me what the number is. What are we doing? So as you can see, each term is 1/3 of the previous term, right? You multiply each term by 1/3 and get the next term. Or it's 1/3 raised to the index. So this one is 1/3 to the first. 1/3 to the second, okay? So in general, a sub n is 1/3 raised to the n, or 1/3 to the n. They're the same. Although this is not our goal, of studying sequences, but these are just few examples. So let's talk about this one. A1, 1, A2, -7, A3 equals, 11. Now someone can tell me what A4 is? How did you come up with 3? Explain it, please. You can open your mic and explain how you came up with 3. 1 negative. Yes. Alex, I can't hear you. Are you talking? Speaking. Nope, can't hear you. You guys hear Alex? No. Alex, yes. I can't hear you. NA, not applicable. I understand how he got 3 though. Well, explain it, please.
Okay, so my thought process was from A1 to A2, that was subtracted by 8, and then from A2 to A3, then we added 18, and then if we followed that again, then by subtracting 8 from 11, then we get to 3.
I mean, that's a, very nice analysis, to be honest. But the answer could be anything because I just made it up, In my mind, I had no pattern between the numbers. But it can be seen that way. So let's go with 3. How about that? So he's saying, the difference between these two is 8. The difference between these two is 18. So we can think of, someone could say, well, the distance here is 8. Then you're adding 10 to the difference. Someone might add another 10 to the difference. So difference between the next two would be 28. You know what I'm saying? So, but, just assume it's 8. They make it 3. How about that? It's okay. But what I'm trying to say, There doesn't have to be any pattern between the terms. Thank you, Max. Alex, was it you're going to say the same thing? Get the same logic? Yep. Okay. Glad we're on the same page. All right. So let me write down what our goal is. So our goal of studying sequences is to find the ultimate behavior, bro, of this sequence, right? And what does it mean, ultimate behavior? That means an infinite horizon, right? Like eventually what the sequence is approaching to. And we have a mathematical notation for that ultimate behavior. What is called the ultimate behavior of a function or a sequence? Starts with letter L. It's called limit. Beautiful. So we would like to know what's the limit of a given sequence n as the index approaches infinity. This is our goal. So, and of course, we care if this converges to some finite value, or does it diverge to maybe infinity, right? Or negative infinity. Then we have another case. Sometimes it doesn't converge to a finite value, nor doesn't diverge to infinity. Sometimes it isolates between two values, or more than one value, multiple values, let's say that. So, or the limit doesn't exist, let's say that. The limit is not unique. How about that? This is a better one. Is not unique. Okay. For example, the sequence we just talked about, like an equals 1 over 2. Did we have that? Or 1 over 3? Let's talk about this. 1 over 3 to the n. The limit of this guy as n approaches infinity is is 0. So it's this case, right? It's a finite value. In fact, if you draw a sequence on the real line, the first one, if this is 0, 1, the first one is 1/3. So it's not even close to 1. It's somewhere here. That's the first one. That's a sub 1. Then I get a, 1/9. That's that guy. And then you have this guy. And then, it's closer and closer and closer and closer. Eventually approaches 0. Right? So this sequence eventually converges. Like there's a point that every element of the sequence gets closer and closer to. Okay. Sam, did you have any question? No. Okay. All right. Let's make another example. Let's talk about this one, like the one that you double the index and you get each time. How about this one? What's the limit of this sequence? Limit of an as n goes to infinity. The answer is infinity. Right? And you can easily see that, 2, 4, 8, 16, and what am I doing? I'm not raising to the second. 2, 4, 6, 8, 10, and so on. So it's just getting larger and larger, right? So if you do, this one, 1 million, then your sequence element is 10 to the 12th, right? I don't even know how to read that one. What's the name of that number? Vigintillion or whatever? Gazillion? I mean, it's the one after trillion. Anyway, so it's getting larger and larger, right? So eventually approaches infinity. This type of sequence, you're not interested at. You might confront them, right? This is the type of sequence we are interested at. Looking for sequences where they convert. Okay? And let's do an example of a case when the limit is not unique. Like you may say it exists, but actually is not the definition of a limit. Limit exists if it's unique. That was one of the necessary conditions for existence or definition of a limit. Here's an example for a limit that doesn't exist. A very simple one, -1 to the n. Okay. So what is a1? -1 to the first, that's -1. What is a sub 2? That's -1 to the second, which is 1. And as you can see, a3, a5, a7, all the odd index ones are -1, and all the even index ones, a sub 4, are all 1. So your sequence, if this is the real line, this is -1, this is 1, jumps, back and forth between 1 and -1. Now, can someone tell me what's the ultimate value of this sequence? Like, what's the value of the sequence at infinity? So the limit of -1 to the n as n approaches infinity does not exist. Beautiful. This limit doesn't exist. So for that reason, this sequence doesn't converge, because if it was converging, it would converge to a unique value. Okay. All right. Question on that? Let's go to the next page. Bottom one. Next page. Let's do 140% and go to top left corner. Good. Let's come up with some of the example of sequences. So more example. Let's talk about this one. I'm using A, you could use a different letter. So let's do B sub n. So B sub n, n plus 1 over n. How about that? Okay. And let's write down, first few terms. So B1 is 1 plus 1 over 1, that's 2. B2 is 3 over 2. B3 is 4 over 3, right? Let's write down next one. B4 is 5 over 4, right? Somewhere along the line, like B50th is 51 over 50. B1000, 1 is 1002 over 1001, right? Always denominator is less than numerator by 1 unit. Now the question is, does this limit converge? And if it does converge, what does it converge to? So we're going to answer this question. Limit of a sub n. Yeah, it goes to 1. It converges to 1, right? And here's the reason. N plus 1 over n, and approaching infinity. Now, thanks to the L'Hopital, you can use L'Hopital, or since it's a rational function, right? We had a technique which was dividing both denominator and numerator by the biggest degree, in this case n. So if you divide everything by n, you get 1 plus 1 over n, and then denominator 1. Right? Let me write down some details. So this is the first one. So divide everything by n over n, plus 1 over n over n, approaching infinity. And as you can see, you have 1 plus 1 over n 1 and approaching infinity, and that's 1 plus 0 because this guy approaches 0, right? When the denominator gets large, the ratio gets smaller eventually approaches 0. So limit is 1. Or someone could use L'Hopital, take derivative both numerator and denominator separately with respect to n to get 1 over 1. Okay. Let's do another one. C sub n being cosine of n pi. And n is a natural number. Remember, n is a natural number, right? So n is 1, 2, 3. So that means the argument of cosine is going to be pi, 2 pi, 3 pi, 4 pi, 5 pi, and so on. Okay, watch it. Does this limit converge? Says no. Why is that? Feel free to open your mic and make an argument. Oh wait, you're doesn't anybody want to take over? Just kidding. You can type Alex if you want. The last time your mic didn't work. I don't know if you were able to figure it out. We're being patient. Yeah, negative 1 to 1 repeated. It's going to jump, back and forth. In fact, I mean, think about it. Let me write down the first few terms. As you can see, C1 is cosine of pi, which is cosine of pi. You mean negative 1? I think you meant negative 1. That's okay. C2 cosine of 2 pi is 1, right? C3, that's cosine of 3 pi. So it goes back, this is the unit circle. Cosine here is negative, and here is positive 1. And as you can see, these are all the odd multiples of pi. So these are all 2k pi's, and these guys are 2k plus 1 pi. So these are all multiples of pi. Those are the side. So it's very similar, to negative 1 to the 1. In fact, it is. The other way to write this is indeed negative 1 to, let me not write it over there since you look at it later. Negative 1, which is negative 1 to the third. This one is negative 1 to the second, and so on. So one can say cosine of n pi is nothing but negative 1 to the n. They're not wrong. They're absolutely right. So these two are the same. And as discussed before, the limit of cosine of n pi goes to infinity, again, does not exist because it isolates between 1 and negative 1, right? Okay. I'm going to talk about a theorem, okay? Well, let me start with an example. Let's call this d sub n. It's 1 over 2 to the n plus 3n. Watch it. Does this sequence converge or diverge? Diverge. How many terms? It is correct. It diverges. How many terms do we see in the sequence? 2. One is 1 over 2, 1 over 2 raised to the n, right? And 3n is the other term. Not both of them diverge. Like if you look at them individually, like separately, one of them converges, right? Which one converges? 1 over 2 to the n. But the one that causes this whole sequence diverge is 3 times n. Okay? So what I'm trying to say is that when we look at the sum of sequences, we look at the behavior of each term, separately. And then we aggregate the total behavior by analyzing the behavior of each term. So, and then if one of them diverges, the whole thing is going to diverge. It doesn't matter if the other ones converge, because one single term is going to, mess up the behavior of the whole thing. So this one diverges. we know this one converges, but it's not going to affect the fact that the whole thing diverges to infinity, right? Basically, 1 over 2n is a core victim of 3 times n, right? That dude is going to just take everything to infinity. And 1 over 2 to the n doesn't have enough power to fight back. So, and this is just a sort of a tease or a motivation for this theorem, and it's a very simple one. You don't even have to memorize it. It's going to write down, and then probably you have seen it before. You have seen it for derivatives. Oh, sorry, I think I messed up everything, but I'm gonna watch the video. Yeah, I've been recording the video. Let's see, have I? Yes, I've been 31 minutes since I missed, the first few minutes. But we're gonna get almost up. Okay. So a theorem is very straightforward, just like I said, you have seen it similar before. Let me write down details. In fact, it's theorem 75 in the textbook. So I'm not gonna write down the whole thing. Just assume you have 3 sequences: A sub n, B sub n, and C sub n. Okay. Then these are true. So limit of an plus b sub n as n approaches infinity. So what is this telling you? It says I'm adding 2 sequences, and then I'm looking at the behavior as n approaches infinity. This is as same as, in fact, this is what we did above, right? Well, check the behavior of each sequence separately, and then aggregate the total behavior by adding the limits. Right? For example, up there are bn, which was 3 times n, was diverging, so makes the whole thing diverge. And same thing is true for subtraction. Okay. And same thing for division, same thing with multiplication. Limit of an times bn as n approaches infinity equals to the limit of an times limit of bn as n approaches infinity. By the way, I have to make an assumption that these, we assume they converge, okay? Because if they diverge, the values are not necessarily the same. Yeah, it is assuming that they converge. So this is number 1. 2, same thing for division, so limit of a sub n over b sub n, which is infinity. It's limit of numerator, limit of denominator. Okay, and approaching infinity. Or an obvious one, if you multiply, the sequence by a scalar, let's say k, it's as same as, look at the limit of the sequence and then multiply by the scalar k. Right? For example, you already know this, limit of 3n as n goes to infinity is the same as 3 times limit of n as n goes to infinity. These two are the same, of course, they're both infinity, but that's what the last one is. Okay. All right. Question. So for the rest of this section, which is short, you mostly doing limits. Okay. Let me remind you definition of a couple functions, and also there was a theorem, so you're gonna find it useful. It's called, I don't know what the book is called, Sandwich theorem or squeeze theorem. Which one did you guys heard? It's the one they talk about here. Squeeze theorem, sandwich theorem. Any of those names ring a bell? You guys? Go back to the last slide really quick. Sure. So really quick. That's your word. Okay. Should I zoom out or should I go to the bottom of the page? Bottom of the page and zoom. There you go. And that is squeeze theorem. You're welcome, Victor. So a squeeze theorem, I mean, the name again is self-explanatory, is that it applies to limits only. So let's say you want to find the limit of, especially it happens when your sequence isolate, like it doesn't have, maybe same sign. Normally happens when you have two different signs, or you have two values and around the two values keeps jumping back and forth. I'll give you an example. I mean, the one example we did was -1 and 1, okay? But there's a condition. So if you have a sequence that you can bound it meaning you can squeeze it on either side with two other sequences. And here's the important condition. The condition is that the outer sequences, the two sequences you're using to squeeze the middle one, those outside ones, they approach to the same exact values. If the outer ones approach to the same exact value, then that middle one is forced, like it has to. There's no way. Like it cannot go, outside that interval. The middle one has to approach the same thing. Here's an example. You good, Vito? Yeah. So thanks. So squeeze theorem. I'm not gonna write it down, so I'll explain it, but I'll write down, the symbols. So let's say, suppose we want to, find the ultimate behavior of the sequence A sub n, right? And then they figure out that A sub n can be squeezed between A sub n and C sub n. And normally, so this is the one that initially we don't know the limit. And B sub n and C sub n, these are the two sequences that you probably already know the behavior. That's why you're getting help from them. So these two sequences are supposed to help you, okay? So we know what the behavior is. Same as Bn. Now, if both of these guys, both B sub n and C sub n, they both approach to, let's say, a common value L, okay? Then think about it. This guy is forced, like it has to. There's no other way because it's squeezed between these two guys. It has to approach to Ln as well. Right? And here's a very simple example. Consider this sequence. -1 raised to the n over, n squared. So when you write down the first few terms of this guy, it's -1 over 1. So it's -1. Then it's 1/4. then it's negative 1 over 9, then it's 1 over 16, then it's negative 1 over 25. So as you can see, the sign changes, right? If I draw it on the real line, the first one is negative 1 is here, then the next one is 1/4, right? So this is A1, this is A2, then A3, right? So it just jumps back and forth, right? Then A4 goes here. And you might be able to say what this one approaches to, right? But the way to argue this, the legit and correct argument is that, well, we know negative 1 to the n is a squeeze between two values. What are those two values? What are the two bounds you can come up for negative 1 to the n? Two numbers, sort of minimum and maximum of this value, of this sequence. Those are negative 1 and 1. Good. All right, now let's go ahead and divide by the positive value of n squared, right? N squared is positive. So there you go. That's the initial sequence A sub n. We were able to come up with two sequences, Bn and Cn. Maybe we weren't able to take limit of A sub n initially, but we are able to take limit of 1 over n squared, and we are able to take limit of negative 1 over n squared, right? So one knows the limit of 1 over n squared as n approaches infinity is 0. Same thing for the limit of negative 1 over n squared as n approaches infinity. That's also 0. So the two middle ones approach to 0. That means, sorry, not the two middle ones, the two outer ones approach 0. That means, so here you can say by squeeze theorem, the limit of negative 1 to the n over n squared is 0 as well as n approaches infinity, right? So that's that. And the other notation that I'm going to talk about is this guy right here. Down right there. So what is that called? Wrong. Exclamation mark. That's wrong. That's 5? That's how you read it, right? 5? I'm kidding. It is called factorial. And what's the meaning of that? So it is called factorial. So let me be more specific. In mathematics, in math, this is called factorial. Now, what's the meaning of 5 factorial? Beautiful. It's multiplication starting from 1 all the way through the number you're doing. Oops. Factorial, right? So it's 1 times 2 times 3 times 4 times 5. And you simply do this multiplication. In this case, I think it's going to be 120, right? So 1 factorial, for example, is definitely 1. 2 factorial is 1 times 2, that's 2. 3 factorial is, 1 times 2 times 3, which is 6, and so on. When especially when the number gets to 6, I wouldn't even bother to calculate it. I think for 6 is 720, but after that I wouldn't. Like 10 factorial is over a million, if not billion. So do not mess with factorial. Like, good luck finding 24 factorial, for example, in your calculator. There's no way. It's going to give you an error, okay? Let alone 100 factorial. In fact, factorial is growing faster than any exponential. There's only one function that grows faster than n factorial. We'll talk about that later and talk about, or maybe tomorrow. So we're almost done. Let me ask you one tricky question. What is 0 factorial? No. Someone said it's 1. Alex? Did you just throw it randomly? Because you said 0 first. The answer is 1. 0 factorial is 1. And actually, it has a very good reason. I'm going to keep your T's until tomorrow. Unless you go look it up. It's very simple. And you look it up. Why is 0 factorial equal 1? Might need a little bit of combinatorics background to see why it is. But I mean, one simple explanation is how many different ways you can have 0 people lined up. So you have no people, and you want to line them up on a on the line. How many different ways can you do it? There's only one way. There's nobody in there. So okay, we're done. Let me ask you one question. Oops. I'm gonna write down the sequence. You tell me what the next value is. So the sequence is 1, 2, 3, 4, 5. What's the missing element on the last box? Okay, more. So it's 1, 2, 3, 4, 5. What's that last missing number? Alex and watch it be 9 for some reason. Not 6. Anybody else want to try it? People do. We only have 6 people. Sam, Max, Ethan, Donovan. Where's Reno? 5. All right, ready? Or you want to think more? Ready? Has any of you driven a manual car? Not auto. Has anybody driven a manual car? No, no. There you go. Ethan got it. Well, cars have, gears. So it has, first gear, second gear, third gear, fourth, fifth. That's the rotation, of that the differential or whatever. The gearbox. But there's one gear missing. What gear is that? That's the reverse one. Told you. Shouldn't be pattern for all sequences. Could be. No, I'm kidding. No, that was just a, brain teasing problem. No, it won't. Okay, so let me zoom out. That was the note for today. I'll make it a PDF, post it on e-learning with the video. Let me go ahead. Pause the video. Stop.